In this video, I'm going to talk about the solution to the Schrodinger equation in one dimension for a free particle. And so, if you remember, we have the time deep or independent, rather, Schrodinger equation, which is this. So then we have the second order differential here. And so usually we would have a plus V, which is our potential here, but since we're in a free particle, we do not have the potential, so that we can set equal to E times our wave function here. And from there, if we do some algebraic manipulation, what we end up with is our second order derivative here being equal to, and I'm going to define a minus k squared, where k is defined as 2m e over h bar, and then this 2me is the square root, because if you see this this h bar is squared, so if you take the square root of all of this, then this just goes to not having an exponent, and this is the square root. But anyway, so we've gone through solutions before, and I will sort of, for that, cut to the chase here. And what we end up with is, if we are looking at the time-independent Schrodinger equation, then we end up with a solution that looks like this, plus b e to the minus I k x. And so in one dimension, what each of these means, so this is a particle moving to the right, where this one with the negative in the exponent is a particle moving to the left. But then we want to add in the time dependence, and I am going to sort of combine those together and say that if we let our k run through positive and negative, that we can end up with something that looks like this. So e to the I, then that k is being distributed in, so we end up with kx, then minus h bar k squared over 2m times t. And so this is our time-dependent solution here. And so when we have the time-dependent Schrodinger equation, the thing that we're looking for is how our system, so how our particle, is actually changing over time. And so for that, we actually need the velocity, since we're talking about a particle that is moving. And actually our particle will be sort of a wave packet that is moving. And we'll see that this wave packet kind of gives it a sort of strange property. And so what I'm going to do is take what we have in the exponent up here, so kx minus h bar k squared over 2mt, and set that equal to 0. So then what we do is divide both sides by t, divide both sides by k. We end up with x over t equals h bar k over 2m. And so what is this? So x over t is just velocity, space over time, so distance over time, so that is equal to our velocity here. And if you remember that we have the momentum, which is equal to h bar k, so this is the momentum divided by 2m here, so it's essentially the momentum divided by 2m divided by 2m. But if you remember that from previous videos, we said that E was equal to the momentum squared over 2m. And so we can rearrange this so that we have the momentum squared equals 2me, and then so we can have our momentum equal to the square root of 2me. E. So we have this here for our momentum being equal to this 2me. And so for that, we can then put v, our velocity, equal to the 2me square root over 2m. And if we just take the square root divided by this, what we end up with is our e over 2m square root. So this is our velocity, and I'm actually even going to specify that this is the velocity q quantum mechanically, because if we look at velocity uh, in classical mechanics, we have 1/2 mv squared, and so this is our energy. So if we multiply both sides by 2, divide both sides by m, and then take the square root, we have v equals 2e over m, and that is the square root. And so this is our v, and I'll put a c here for classical, where we had our v for quantum mechanics being equal to e over 2m square root. And so what you see is that we have the 2 in the denominator here and the 2 in the numerator for classical. And so this is kind of weird. So how is it that our quantum mechanical velocity is different from our classical velocity? And so the answer is that our quantum mechanical velocity is actually telling us what I'm going to call phase velocity. So I'll put a little p here. And we will also have what is called the group velocity. So phase velocity and group velocity. So we can actually see the difference here if we look at the Wikipedia page for group velocity. You can get the same thing from the phase velocity. So the group velocity and the phase velocity, they both have this same little figure here. And so this is different because this shows with the red square here the phase velocity, and the green the group velocity. And on this is showing the phase velocity being higher than the group velocity, whereas in our system we know that the phase velocity, which is our quantum mechanical velocity, is actually less than our group velocity, which is our classical velocity, because we have the 2 in the denominator here. And so this is obviously a possible thing, but it doesn't have to be this way. And in fact, this figure down here kind of shows something interesting, that we can have the group velocity, which is traveling to the right, be going in the opposite direction of the phase velocity, which is actually traveling to the left in this figure. So the group velocity and phase velocity can be at different magnitudes and in different directions. So the group velocity, though, is telling us how fast the wave packet itself is moving, where the phase velocity is telling us how fast sort of a single wave length is moving. And so what is kind of happening here is, if you remember, a wave packet is made out of a bunch of different wavelengths. So we have a wavelength here, then we have sort of a different wavelength here, then even sort of a different wavelength here. And these all sort of combine together to give us this wave packet here. And if you remember, each of these sort of plane waves tells us a different momentum, where this is telling us the position. So the position is x. So the momentum is related to the wavelength. So different wavelengths are different momenta, where each of these is sort of a position. And I talked about this in a previous video, how this is related through the Fourier transform. And so we have our time-dependent Schrodinger equation here, and that is going to be equal to some normalization factor here. And so we're doing a summation, but it's a continuous summation uh, of these different momenta here. So we're summing together, and that's what an integral is a continuous summation. We're summing together a bunch of different momenta, and so the momentum is our phi here, which the k, so k, if you remember, is also related to the momentum. I mean, I can even put it, it's h bar k. So the k is, equal to the momentum over the h bar. So the k is related to the momentum, and that's what this right here is telling us. And then we have our e to the the I. Oops, that should be a kx, and then we have minus, and I'm going to put an omega here, and I'll explain that here in a little bit, and then dk. And so this here is our momentum, where this here is our position, and they're related to each other through the Fourier transform. And so this is going to be then equal to that normalization factor here, then minus infinity to plus infinity, and this is over position, so this is summed over position, and then that will be our wave function, and it's going to be the wave function at some specific time, so at t equals 0, and then e to the minus I k x, and then dx. And so this is related through the Fourier transform, so ft. And this is also telling us, remember I said in a previous video that this is sort of an interpretation of the Heisenberg uncertainty principle. And we can actually look at that. This is a figure from the Griffiths textbook on quantum mechanics. And so we see here, if we have the position well defined, we have this nice well-defined position here, then through the Fourier transform, so if we Fourier transform it using those formula that I was just talking about before, we get this spread out, momentum here. And so each spot here is a different momentum. So that's a momentum, that's a momentum, that's a momentum, that's a momentum. So this is sort of a bunch of different, this is all the different momenta that are being summed together. Remember, our wave packet is a bunch of different momenta being summed together, coming together to form our wave packet here. And so this, each spot on the x-axis here is a different momentum, and what's on the y-axis is how much that momentum is contributing to our wave packet. So that would be sort of the amplitude. So momenta around this point here would have much higher amplitudes, where momenta, say like right here, would have much smaller amplitudes, but they would be higher frequency as you go out in the different directions. And the difference in direction is sort of the phase difference. But anyway, that is sort of where our Heisenberg uncertainty principle comes from, which, if you recall, for position and momentum is the uncertainty in position times the uncertainty in momentum is equal to h bar over 2 pi. But I'm not going to get too deep into that. I've talked about it in previous videos. Uh, but anyway, so we have our phase velocity and our group velocity. And the phase velocity is going to be, so Vp is going to end up being equal to our omega, which is a function of k over k. And so that omega is the omega that I used up here. So the phase velocity is the omega, which is a function of k over k. And the group velocity is actually going to be the derivative of our omega k with respect to k. And so what we end up with here is our h bar k over 2m. Because remember, in this over here, or where was that? Yeah, so the h bar k, so it was h bar k squared here. So if we're dividing by k, then that k goes away, and we end up with our h bar k over 2m here. And our group velocity is going to end up being h bar k over m. And so we see that our phase velocity is half the group velocity. So and so what that ends up being is we have our phase velocity being 1/2 our group velocity, or you could say equivalently that the group velocity is twice the phase velocity. So anyway, that's how we end up with our two different velocities. Like I said, this one shows the phase velocity being higher than the group velocity, but in our system it is the group velocity that is higher than the phase velocity. And that's essentially telling us that if we have sort of this plane wave, which is one momentum, and that would be moving in this direction, and we also have, some other frequency moving in that direction. These are moving, and then these come together so that they form our wave packet. The speed at which these are moving is half of at which the actual particle, the wave packet, is moving. And it's the movement of these and sort of their differential phases and frequencies and so forth that actually causes the movement of the particle. So as this moves and this moves, the interference is sort of altering between these different frequencies, and that is what is actually causing the particle to move. And so yeah, that is a free particle in one dimension. In the next video, I'm going to look at what happens if we have a delta function potential. And so that is essentially having a potential being equal to 0 here and being equal to 0 here and then being greater than 0 here. And we have our particle coming in, and it will come and it will run into this potential here. And you would think in classical mechanics what happens is if you have, say you have sort of a ball inside of here, or I guess if we want to think about it more in terms of that, if we have a ball and we have some wall here, if you throw the ball, if it doesn't have enough energy, it's just going to bounce off the wall. And so there has to be some energy that would allow it to sort of, I guess, break through the wall, sort of break through the barrier, the potential that's stopping the ball from moving through. Where in quantum mechanics we have what is sometimes called quantum tunneling, and so some of the wave particle will transmit through, and some of it will be reflected back. And so that is what we will talk about in the next video. So anyway, I hope you found this video helpful, and I will see you in the next one.